So the next addressing mode used in 8086 is addressing modes for input output, in which how the input and output devices can be used for addressing purpose, so that either the information can be taken from those devices or information can be given to that devices. So the first one is the direct input output port address, in which we used to define the address of the port directly within the instruction. The first one is in AL in the bracket 09. Now this 09 represents the port address. Of course, whenever we write in instruction along with AL, so this can be along with 09. 09 is representing port address and it has to be within the bracket. So what does it mean? It means this is the source and you want to copy it into the lower accumulator. So the port address is 09. So whatever is the content of the input device whose port address is 09, it will be copied in the AL register. Now there is a facility in 8086 to provide the port address indirectly. Without writing the address directly, we can write the address where the address is present. Suppose I have written out dx-ax. So what this instruction means, we want to copy the content of accumulator to the output device, but we don't know the address of the output device. It means we don't know the port address of the output device. Now the port address of the output device is defined within a register, 16-bit register, that is DX. So in this case, the port address is 09, which is directly defined. So it is in the direct addressing mode. And in this case, the port address is not defined directly, but it is indirectly defined and saying that DX contains the port address. So port address is DX. So whatever is the content of AX, it will be copied to a port whose address is present in the DX register. Now the next addressing mode is relative addressing mode. In this relative addressing mode, the effective address of a program instruction is specified relative to the instruction pointer by an 8-bit signed displacement. So what does it actually means? If I write an instruction like this, JZOA 0A, jump on 0A. So it means 0A is the displacement address. So first of all, 0A is converted into 000A, and then since it has to jump to a certain instruction which is written somewhere in the memory, and you have to find out the address of that memory. Normally, whenever we have to fetch the instruction, the code segment register will be giving the base address and the instruction pointer register will be giving the effective address. But in relative addressing mode, you can write it like this. It means this is the displacement. So it means the effective address will be calculated by content of instruction pointer plus 000A, which is defined within the instruction. And then base address is available in the code segment register. It is shifted 4-bit left, and then it is added with the effective address to get the physical address or the memory address. So if zero flag is set, if zero flag is 1, then instruction pointer plus 000A will become the instruction pointer. Whatever is the content of instruction pointer is modified by this value 0A, that is 000A. And the program control jumps to this new address which is being calculated. Now, if this instruction is not true, means this zero flag is not set, is this condition is not true. It means zero flag is not set. If zero flag is not set, it will not increment the content of instruction pointer by 000A. The effective address will be changed from IP content to IP plus 000A if and only if the zero flag is set. If the zero flag is not set, the next instruction written after the jump on no zero, whose address will be present in the instruction pointer, will be used as a effective address. So this kind of addressing mode is called relative addressing. So this is about the addressing modes related with input output device and the relative addressing mode in case of branching, conditional branching. And the last addressing mode of 8086 is the implicit addressing mode, in which in this mode, the instruction itself specify the data to be operated by the instruction. There is no need to specify the operand in that particular case. For example, CLC. CLC is a kind of an instruction which is going to clear the carry flag. So it is not necessary to define, only the opcode is more than sufficient. So it implicitly means, see, whenever we write CLC, it implicitly means that carry flag has to be reset. Very much similar to the some instructions which are used in 8085. For example, CMA. CMA stands for complement, and it is implicitly defined that it will take the complement of the accumulator. Similarly, in 8086, we have implicit addressing mode in which this kind of instruction is used, in which there is no need to specify the data on which it has to operate. If it is written CLC, it will clear the carry flag. So with this, that is all about the addressing modes which are used in 8086. Now, the 8086 pin diagram, because the architecture of 8086 must be known. So what is the, it is also a 40 pin configuration. 8086 is also having 40 pins, and these pins are signified by this. The pin number 1 is a ground. From pin number 2 to pin number 16, it is identified as AD0 to AD14. Whenever it is writing AD, it means it is working as an address, or it will be in an, as well as it is working as a data. So this pin number 2 to pin number 16 is meant for address of linked data bus, and it is from D0 to D14 or A0 to A14. NMI stands for non-maskable interrupt. INTR stands for interrupt signal. This is for the clock. This is for the ground. This is 21 is for the reset, ready, and this is used for the test. The pin number 24 and 25 is again a kind of status signal, which is QS0 and QS1, and pin number 25 also works as ALE, and pin number 24 also works as INTA. Now, why these configurations are written? Because I have already told you that 8086 works in two modes. One is called maximum mode and another is called minimum mode. Minimum mode of 8086 is used in a smaller system, but if the system is complex and it has to handle many things, in that case we use maximum mode. So whatever signals are written in within the bracket, such as INTA, ALE, DEN, DT/R, memory input output, write, HLDA, hold, all these signals will be used at the pin number 24 to pin number 31 if 8086 is working in a minimum mode. Otherwise, if 8086 is working in a maximum mode, then QS1 pin number 24 will be working as a QS1 pin, then QS0, and so on. Similarly, pin number 32 is meant for read. This 33 pin number is going to define whether it is working in a minimum mode or in a maximum mode. If it is 1, it is high, it is working in a minimum mode. If it is low, it is working in a maximum mode. Pin number 34 is bus high enable signal, and it is multiplexed with S7. This is another status signal. Pin number 35 is address bus A19 to A16 from 38 to 35, and S3, and these are time multiplexed with S3, S4, S. All these S3, S4, S5, S6, S7, all these are the status signal. And pin number 39 is meant for AD15, and pin number 40 is the power supply, that is VCC plus 5 volt. Now, in 8086, we have 20 address lines. You can see, if I consider A0 to A14, then A15, 16, 17, 18, 19. So A0 to A19 is the 20 address lines. And we have 16 data lines from D0 to D15. So it means the 20-bit address lines consist of two parts. One is called higher order address line and another is called lower order address line. Higher order address line belongs to A0 to A15 is called higher order address line, and A16 to A19 is a lower order address line. Higher order address lines are time multiplexed with data lines from D0 to D15, and and the A16 to A19 is time multiplexed with the status lines. So now let us go for the discussion on the individual pins. What is the working of those pins? So first of all, I will be discussing AD15 to AD8. Now, 8086 address oblique data bus lines, it is composed of upper multiplexed address oblique data bus. This is AD8 to AD15. Now these lines contains the address bit from A15 to A8 whenever the ALE signal is high, that is of the logic 1, and data bus connection from D15 to D8 when the logic pin is 0. So whenever ALE is at the logic 1 and data bus connection D15 to D8, now these pins are going to enter into high impedance state whenever hold acknowledged signal used to occur. So actually it means that from AD0 to AD15 at a particular time, it is working as a A0 to A15 sending the address bus, and the next time it will be used as D0 to D15 for carrying the data from the microprocessor to the rest of the device or from the rest of the device to the microprocessor. Now, what is about the status of A16 to A19, which is time multiplexed with the status signal S3, S4, S5, and S6? This address oblique status bus are multiplexed to provide the address signal from A19 to A16 and also the status bit, that is S3 to S6. Now, this pin also attain a high impedance state during the hold acknowledge signal. So whenever there is a DMA data transfer operation, these pins are in the high impedance state. Now the status bit, this S6 status bit, this status signal S6 always remains at the logic 0, and bit S5 indicates the condition of the interrupt flag bit, and S4 and S3 is going to show that which segment is accessed during the current bus cycle. So S3 and S4, the combination of X3, S4 is going to give the information that which segment of the memory will be used. Suppose S3 and S4 are 0, 0, then it means it is working with it has to work with the extra segment. If S3 is 1 and S4 is 0, it will working as a stack segment. If S3 is 0 and S4 is 1, it will be interacting with the code segment. And if it is both the S3 and S4 are 1, 1, it is working with the data segment. So S3 and S4 are going to give the identification that with which segment, the address which is going, it is working with which segment, whether it is working with the data segment, extra segment, code segment, or the stack segment. And the combination of S3 and S4 is going to define that. Then we have a read signal. Now, whenever this read signal is at logic 0, the database is to read the data from the memory or the input output device which is connected with the system. Now, this pin is again going to be flowed into high impedance state whenever there is a hold acknowledge signal is there. So the purpose of this read signal is to read the information either from the memory or from the input device. And it has to be low at that time. Then let us discuss about the ready signal. Now this input signal, this ready signal is an input signal to the microprocessor. This input is controlled to insert the microprocessor into a wait state. And whenever this ready pin is placed at a logic 0 by the microprocessor, by the external devices, the microprocessor is going to enter into the wait state and will remain ideal until the ready pin is placed at logic 1. So it means this ready signal is used by the external devices to make the 8086 in the ideal state and wait for the information which is being flowing from the peripheral devices. Actually, this signal is used to make it compatible, because compatibility with the external devices, because as far as the speed of 8086 is concerned, it is good enough in comparison to the speed of the peripheral devices. So whenever peripheral devices, if the 8086 is ready to receive the data, for example, and peripheral devices are not ready to give the data at the same time, then what it will do, it will put the 8086 into a wait state by putting the ready signal low. And when the information is available to transfer from the external device to the 8086, it puts the ready signal at the level of 1. Then let us discuss about the INTR signal. This is an interrupt request which is needed to request a hardware interrupt. Whenever any device wants to interrupt the operation of 8086, it has to make a request with this INTR pin. It is again an incoming pin to the 8086. So it is a kind of a request which is given by the external device who wants to interrupt the operation of the 8086. Now, this INTR line is going to become high. It is on the high state if the interrupt flag is 1. And 8086 is going to enter into the interrupt acknowledge cycle. That is, INTA becomes active and after the current instruction is completed. So whenever any device wants to interrupt, it will send an interrupt signal high to the 8086. And what will happen if, suppose, microprocessor is doing something, is processing something, it will finish that processing, then it will entertain the INTR, and then it will send an interrupt acknowledge signal to that particular device who has sent this interrupt. Then the next signal is the test signal. Now test pin is on the input, and that is tested by the wait instruction. This is being tested. This is again an incoming pin to the 8085, and it is going to test the wait instruction. If this test is at the logic 0, it means whenever it is low, the wait instruction functions as a no operation. Whatever is the wait instruction, it is working as a no operation. But if the test is at the logic 1, the wait instruction waits for the test to become 0, and this pin is most commonly used whenever 8086 is working along with co-processor, that is 8087, that is also called mathematical processor, or you can say numeric processor. 8087 is another kind of a processor which is designed by 8086, which works in constituent with the 8086. And the purpose is to do the mathematical operation. That is why it is called the math processor. So whenever 8087 has to be used, then only this test pin will be used. Then we have another pin, pin number 17, that is non-maskable interrupt. Now, non-maskable interrupt is just similar to the INTR, except that these two, INTR and MIR, seems to be similar. But the non-maskable interrupt does not require any checking, because INTR signal, whenever it is going high, it has to check whether the interrupt enable flag is set or not. But whenever any information, any signal is coming into the NMI, that is non-maskable interrupt, it has to entertain it. So when the NMI is activated, this interrupt uses interrupt vector 2. Now there are many vectors which can be used for that. INTR is a general one, and NMI is so the next instruction is reset instruction. The working of this reset instruction is very much similar to the reset instruction used in 8085, and the purpose is to reset all the operations of 8086. So this is going to reset the microprocessor if the reset pin is high, and whenever any device wants to reset the operation of 8086, it will put this signal high, otherwise it will work as. So whenever the operation of 8086 has to be reset, this signal will be worked. Then we have a clock. This clock pin will provide the basic timing signal to the microprocessor, and this clock signal must have a duty cycle of 33%, which is high for 1/3 of the clocking period and low for the 2/3. So it is just to provide the proper internal timing as far as the 8086 is concerned. VCC is for the power supply. Of course, it works on +5 volt. GND is for the ground supply to the microprocessor. Minimum and the maximum pin, which is the pin number 33. This maximum and the minimum pin is going to select the mode in which the microprocessor will be working. Either it will be working in a minimum mode, or it will be working in the, so whatever operation we want to perform by the microprocessor, accordingly this signal will be high or the low. If it is high, it is working in a minimum mode. Whenever it is low, it is working in a maximum mode. So when minimum mode is selected, the minimum/maximum pin input is connected directly to the +5 volt, because it requires the high signal. Then we have a signal bus high enable signal /S7. S7 is a status signal, and bus high enable signal is very much similar to the ALE signal of 8085. Now this bus high enable pin is going to help the 8086 to enable the most significant data bus bit, that is D15 to D8, during a read or the write operation. And the state of S7 is always remains at the logic 1. As the status of S6 always remains at 0, S7 always remains at 1. So this is the explanation of as far as the different pins of 8086 is concerned. Now let us discuss with the minimum mode pins. The minimum mode pin, if you go through these are the minimum mode pin which I have not discussed, such as hold, HLDA, write, memory input output, DTR, DN, ALE, and INTA. So let us go one by one and discuss. The hold signal, whenever any device wants to transfer the data without any intervention of 8086, it will be using the direct memory access data transfer scheme, by which it will be transferring the data from one place to another place directly. So for that particular purpose, it has to send a hold signal to the microprocessor. And once the microprocessor is going to receive this instruction, this information from any device, it acknowledges with the help of hold acknowledge signal. So this hold input request, hold input is a request by external device for a direct memory access data transfer, that is called DMA data transfer. Now, if this hold signal is at the logic 1, the microprocessor stops its execution, whatever it is doing, and places the address bus, data bus, and control bus into a high impedance state and going to allow the external devices who has put the hold signal to use those address bus, data bus, and the control bus to take these control into its position so that it will be able to transfer the data directly without any intervention of 8086. And in reply to that, for acknowledging that it has received a hold signal and relieved the control bus, data bus, and the address bus, it will send a hold acknowledge signal to that particular device. So it means for getting a hold signal should be high, but whenever the hold signal is low, it means 8086 will be working in its, it will be doing its own operation. Write signal, WR. The WR line is a strobe that indicates that 8086 is going to output some data to the memory or to the input output device. So at the time when the write signal is at the logic 0, the data bus contains valid data either for the memory or for the input output device. Now this pin floats a high impedance state during the hold acknowledge signal. Whenever hold acknowledge signal is being sent by microprocessor, this signal is going to be in the high impedance state. But whenever it is the normal working, it is going to give the information that whatever is the content of the data bus, it is meant for either for the memory or for the input output device. Then we have memory oblique input output or input output oblique memory, whatever you say. This memory oblique input output pin is going to select whether it wants to work with the memory or it wants to work with the input output device. So it means this is going to indicate that the microprocessor address bus contains either a memory address or it is an input output port address. So this is going to identify whether it is want to work with the memory or it wants to work with the input output device. Then we have DT oblique R. DT oblique R means data transmit. DT stands for data transmit and R stands for receive. The data transmit oblique receive signal, it shows that the microprocessor, the data is being transmitting if it is at 1. And it is on the receiving mode if this signal is low. So actually this signal is used to enable the external data bus buffer so that whatever data has to be received by the 8086 or whether whatever data has to be transmitted by 8086 has to be stored in the buffer. So this is just an information to enable the buffer so that whether the data which has been transmitted should be buffered or the data which is required to be received has to be buffered. Then we have another signal, it is called DEN signal. Now DEN signal stands for whether it is going to enable the data bus or not. Data enable bus, data enable line. So data bus enable activates the external data bus buffer. So this signal is used to activate the external data bus buffer. And the last one is ALE signal. I have already explained that it is address latch enable, and it shows that 8086 the address oblique data bus contains whether it is containing the address information, where the address can be a memory address or it can be an input output port address. Whenever ALE signal is high, it will be the address which will be placed on that bus. If it is low, it means it is now ready to receive the data on the address oblique data bus. INTA, this is an interrupt acknowledge signal. Whenever any interrupt is going to be received by 8086, it is being acknowledged by interrupt acknowledge signal. So this signal is going to give acknowledgement or in response to any interrupt line to that device. So this INTA pin is normally negatively activated pin and is normally used to gate the interrupt vector number onto the data bus in response to the address, in response to the interrupt. So whenever, so meaning thereby, whenever any device wants to interrupt and it wants to activate certain subroutine, that is called service subroutine. So whenever it wants to activate certain subroutine, the subroutine will be written in somewhere in the memory and it has certain address. So actually, while acknowledging the signal, the time has come to store the address of that subroutine on the bus. So it is the pin which normally gives the acknowledgement of the interrupt signal received by external device. Then we have another signal. Uh, all has been explained. So tomorrow we will be